Good afternoon, Year 9. Welcome back to your part 5 of computer science, binary representation and compression. Last week we looked at lossless compression, where it makes a file size smaller without losing quality, and lossy compression makes a file size even smaller than lossless, but you lose quality. So it's like taking out pixels and stuff like that. Today I'm going to give you a brief overview of sound, and then in lesson I'll be able to demonstrate it a bit further on how microphone works. I'll be showing you about sound waves and how you can manipulate sound waves and code sound waves. I'll also bring in a club light, which demonstrates how that microphone detects that sound. So the idea of today's lesson is to build that foundation there, and then in lesson, we can then cover it even further. So it's a nice short lesson. There's not much work to do, but it is a few things that you just need to know before going into the sound lesson when you're back at school. So let's get started. It says, how is sound recorded? Well, basically, you have a microphone, and I'm talking to a microphone right now. It's just here, just there. And basically, there's a coil in this microphone. And what happens is that every time you speak into it, it creates a sound wave. My diaphragm vibrates. And it pushes down on this coil. When it pushes down on that coil, it measures that sound wave and records that sound wave. So basically, a sample is basically sound, which is stored in binary, and little segments of the sound wave are recorded, which are called samples. So the higher the sample rate, the higher the quality. So if you look at this just picture here, I've got a low sample rate here. So I'm only recording the elements of the sound wave when you see a straight line on the bar. So I've recorded here, recorded here, recorded here, recorded here, and so on. But the problem is with this, what happens is you skip areas of that sound wave. So say if this sound wave was going like that, with the sample rate being lower, instead of the nice build-up of you'll just get like that. So it just jump really quickly. So you'd have like loads of jumps in your sound. It would sound like something sticking on the CD. So you need a higher sample rate to capture that growth in that sound wave instead of just going from low to high up here. So you need a high sample rate, because if not, you're going to lose that quality on that sound wave. So the sample rate is basically a binary value which is stored. So that sound is converted into digital, which is binary. So analog is basically, I'm talking in analog right now because my diaphragm is vibrating. Fun fact as well, when you're on a phone call, how you actually sound on the phone is how you actually sound to other people. When you speak, your skull vibrates, and so you don't hear your own voice properly. So how you sound on the phone is how actually everyone hears you. I know a lot of people don't like their phone voice. I certainly don't like mine, but I'm now used to it. So basically, I'm talking analog right now. My diaphragm is vibrating. It's analog sound waves. That's recorded inside of the computer in binary, which is called analog to digital. And then what happens is that when we want to play that sound out of a speaker, so when you're playing this right now through your headphones or through a speaker, what happens is the speaker has its own man-made diaphragm with magnets that pulses out, acts like a diaphragm vibrating, and recreates that sound. So then it goes from digital to analog, so we can hear it normally. So we record sounds with samples. The higher the sample rate, the more quality of sound. Can you please write down this bullet point and copy down that picture to show a low sample rate and how it's missed those parts of the wave, and then a high sample rate on how it's hitting those parts of the wave much more, and so you've got more quality sound. Pause the video and then come back. All right, so there's loads. So like with last week, we looked at pixels and how we have different colors for a pixel. It's the same in sound. So we have different amounts of sound based on the amount of bits we have. So if in a pixel, if we have 3 bits per pixel, we've got 8 colors. Same with sound. If you've got 3 bits of sound resolution, which is called audio depth, you have 8 possible sounds that you could use. It could be beep, bop, beep, bep, 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 or whatever. So that's when you've like seen like I don't know, like 8-bit sounds versus 24-bit sounds and so on and so forth. So this is called sound resolution or audio bit depth. If the sample resolution is 3 bits, you've got 8 possible sounds. The higher the sample resolution, the higher the quality. So if we look at this picture just here on the 16-bit side, it's not very good quality at all because we can only make those sounds that reach that part of the sound wave. Whereas on the 24-bit sound, it looks nice and smooth because we're matching to all of those sounds. So the higher the sample resolution, then the higher the quality of the audio file will be. So do go on YouTube and have a look at some 8-bit sounds versus 24-bit sounds. I will show you in lesson as well, and we'll manipulate that audio bit depth and sample resolution to show you the difference in quality of a song. You really will notice it. The bit depth is really significant, just like the amount of bits per pixel is significant for an image. All right, so again, can you write down all of that and draw the picture to show and demonstrate how that quality of sound will be different. So pause the video and then come back. All right, so file size. To calculate file size is very much the same as how we calculate image size. With image size, you calculate the bits per pixel, the width times the height. Here we've got the sample rate, so how many samples you take in per second. The sample resolution times by the sample resolution, so it could be like 3 bits, and then the length in seconds, so say like 3 seconds. So if I've got a sound file which has a sample rate of 10, so that's 10 samples per second, and the sample resolution is 2, so that's 10 times 2, which is 20, and then the length of the song is 5, then therefore you've got 100 bits. So therefore, we always like to convert to bytes as well where we can, so we divide that by 8, so 100 divided by 8, half it, 50, half it, 25, half it again, you've got 12.5 bytes. All right, so please do make that nice and red and bold and big in your book so you remember it. You need to remember this formula. It is very prevalent in the exam. All right, so sound compression, how to make a sound smaller, how to make a file size smaller. If you're using lossy compression, the most common one is an MP3. And basically, it reduces the quality, but the majority of the data that's lost and it takes sound out is the sound that humans can't hear. We can only hear between 20 hertz and 20,000 hertz. So if there's any sounds above that or below that, we won't be able to hear it. So with MP3, they take the majority of that sound out. They also take some sound out between our hearing range, but the majority of it is taken out above our hearing range or below our hearing range. So yeah, the nice little facts about MP3 just there. All right, so I've got a little task for you today. Can you please answer the following questions? I would like you to calculate the file sizes. So the sample rate is 6, the sound resolution is 3, and the length of the audio file is 2. Calculate that file size. Then the sample rate is 10. There are 8 possible sounds. So if there's 8 possible sounds, how many bits would you need? What would your audio bit depth be? And then times by 3 seconds. And then we've got the sample rate is 5. There are 4 possible sounds, so you need to calculate what the audio bit depth would be, and the length of the audio is 1 minute. Now, don't forget, we look at the amount of seconds, so you need to convert a minute into seconds. All right, so pause the video, answer those questions, and then we'll go over the answers. All right, so the answers are, we have, firstly, the top one is just literally 6 times 3 times 2 is 36, and then you divide that by 8, so you half it, which is 18, half it, which is 9, half it again, which is 4.5, so it's 4.5 bytes. The sample rate is 10. There are 8 possible sounds. So if it's 8 possible sounds, that's audio bit depth of 3. And then you need to times that by 3 again. So 10 times 3 times 3 is 90. Divide that by 8, so half it, half it, half it, and you get 11.25 bytes. The sample rate is 5. There are 4 possible sounds. So if it's 4 possible sounds, the audio bit depth is 2. And the length of the audio is a minute, so that's 60 seconds. So 5 times 2 times 60 equals 600 bits. And then that equals 75 bytes. All right, guys, that marks the end of the lesson today. Nice small amount of facts, but you need to remember these facts before coming into the lesson. And I will show you a bit more in depth about sound, show you some awesome videos I have about it as well. And it'll be good for that foundation there for that recap. So let's have a look at the fact book. So we have covered absolutely lots of stuff this term through remote learning, which is great. It's been so good seeing all of your work that you've been doing and sending me. Keep up the good work, keep going with it. So we converted, we looked at the start and we looked at how to convert with all of binary and stuff like that. Before you come back in September, if you're unsure on any of that, you need to watch the video again and practice. It's nice and easy to practice. All you do is anyone in your household say, give me a number between 1 and 255. Then convert that number to binary, then convert that number to hexadecimal. Ask for 2 numbers, convert them to binary, then add them together. It's nice and it's a nice way of practicing. You need to keep on revising that. Then we looked at the logic gates and how there's millions of logic gates in a computer and what each one does and how to put them together, looking at the symbols. That was a really tough lesson. Then we had a shortish lesson on ASCII and Unicode, so how characters on a keyboard are converted to binary and stuff like that. Don't forget that ASCII is limited on the amount of characters you can have, but you'll have a smaller file size. Unicode is, you're not limited on characters because you've got 65,536 possibilities. However, your file size is bigger. You've got lossy and lossless compression. Lossy makes the file size smaller, quality is lost. Lossless makes the file size smaller, quality is not lost. So for like MRI scans and stuff like that, you would need it, and books and source code. Whereas images and videos, you can use lossy compression on that because, you know, at the end of the day, it doesn't really matter. Sound is stored in binary. Sound resolution is the number of different sounds available. Sample rate equals the amount of sounds recorded per second. You've got your file size formula just there. And to understand the different methods of sound compression, we'll go into more detail in that in lesson, but the MP3 one is pretty good. It's a lossy compression algorithm. All file types are just literally compression algorithms that people have made, and that's what a file size is. Like a JPEG image is a lossy compression algorithm that just removes colors from an image or maybe pixels from an image. All right, so that marks the end of our lessons this term. So I'd like to say very, very well done, guys. I cannot wait to see you back in September. I'm so looking forward to it. I think it's going to be an amazing couple of years working together. And if there's anything you need in the meantime, please do drop me an email. Have a wonderful summer holiday. There is a quiz to complete. If you can complete it, that'd be great. Have a great summer holiday. Keep doing the good work that you have been doing. See you in September.